Here we're going to look at a nice problem from a math contest from China in 1996. That's all the information I have. I don't know exactly what math contest it was or the name of the math contest or anything like that. I just know that it was in 1996 in China. So let's look at the statement. So we want to let n be a natural number, so in other words, a positive integer. And our goal is to find the number of polynomials p of x with coefficients from this set of four numbers, 0, 1, 2, and 3, such that when we evaluate p at 2, we get n. So I'm going to give you guys some hints in order to solve this, but I should say that the hints might give it away a little bit if you are well trained in the topic of math contests. If you're not well trained in all of the tricks that are common in math contests, then you might need them. But, you know, if you're well trained, maybe skip these hints and just try the problem on your own. Okay. So my hint is to translate this into a question about integer partitions. So those of you who are well trained in math contests will know tons about integer partitions because they show up from time to time in math contests. But let's just recall what it is. So we say lambda is a partition of n, and we use this symbol right here. If lambda is an m tuple, so that could be a 1 tuple, a 2 tuple, and so on and so forth. So we'll denote it lambda 1, lambda 2, all the way up to lambda m, such that these numbers sum to n, and they form this decreasing, or I should say non-increasing sequence. So lambda 1 is bigger than or equal to lambda 2, which is bigger than or equal to lambda 3, and so on and so forth. And so just as an example, this triple 4, 3, 1 is a partition of 8. So it obeys this rule right here, and 4 plus 3 plus 1 equals 8. So again, my first hint is to translate this into a question about integer partitions. And then when you're looking at integer partitions, there are a couple of tools that you could use. You could use these things called Farrer's diagrams to analyze a problem involving integer partitions, or more likely in a math contest, you'll use generating functions. So that's my second hint, is to think about generating functions. So just as an example for how this would work. So again, if you've seen a lot about integer partitions and their generating functions, then this example is not super necessary, but just in case you haven't, this is a nice example to think about if you want to try this problem. So if we want to let f of n, so little f of n, be equal to the number of partitions of n using only 2's and 5's with at most 2 5's. So it's hard to get a handle on what that number exactly is with some sort of formula, but writing down a generating function is actually pretty easy. So the generating function will be like this. So it'll be the sum n equals 0 to infinity, f of n, q to the n. So the coefficient of q to the n is this value of f of n that we're looking for. And you can see that this is going to be equal to 1 plus q squared plus q to the 4th plus q to the 6th, and so on and so forth forever, times 1 plus q to the 5th plus q to the 10th. And here, each of these terms controls how many 2's we're using. And over here, each of these terms controls how many 5's we're using. So if we take the product of, for instance, this guy right here with this guy right here, that would correspond to a partition of 7. And it's the partition of 7 where we've used a single 2 and a single 5. So in other words, 5 plus 2. So a lot of times when we're dealing with these generating functions for partitions of a certain number, we want to simplify them into some sort of nice rational function, and that's what you can do. You can take this first bit and rewrite it as a geometric series 1 over 1 minus q squared, and that allows you to write this whole thing as 1 plus q to the 5th plus q to the 10th over 1 plus q squared. So I want to point out that this first thing is an infinite sum because we're allowing as many 2's as we want. But the second thing is a finite sum because we have at most 2 5's. So we go up to the power of q to the 5 quantity squared. So that would correspond to a partition using 2 5's. Okay, so I'll go ahead and clean this up and then we'll look at a solution. So hopefully that hint was helpful. Now we're ready to look for a solution. So let's go ahead and take one of these polynomials. So we're gonna set p of x equal to a0 plus a1x plus a2x squared all the way up to amx to the m. And here I have all of these numbers, a0, a1, a2, all the way up to am are from this set 0, 1, 2, 3. So I'll just write that as ai is in the set 0, 1, 2, 3. Now, since we want to look for the natural numbers that can be expressed as this polynomial evaluated at 2, let's go ahead and evaluate this polynomial at 2. So if we evaluate this polynomial at 2, let's see what we get. So we'll get a0 plus 2a1 plus 4a2, in other words, 2 squared a2, plus 8a3, in other words, 2 cubed a3, all the way up to, what do we have at the end? We're going to have 2 to the m, a sub m. Now, I want to point out that if this is equal to n, then it is in fact a partition of n satisfying some certain rule. So let's think about what rule that it must satisfy. Then maybe we can write a generating function for that rule. So this is a partition of n, and maybe the rule is a bit tricky, but the easiest thing to see is what parts we are using. And notice we are using parts that are powers of 2. So let's write that down. So with parts 1, notice that's 2 to the 0, 2, 4, 8, 16, and so on and so forth. So in other words, with parts that are powers of 2. And then we also can figure out how many of each part we're using, and that is governed by this coefficient here. So notice if a0 is 2, then we're using 2 parts that are equal to 1. But then for instance, up here, if a3 is equal to 3, then we are using 3 parts that are equal to 8, because that's the coefficient of 8 here. So let's maybe encode that in this sentence as well. So each part used 0 to 3 times. So sometimes this is written as repeated at most 3 times. So now that we have that, we can go ahead and start to form a generating function. So let's maybe introduce some notation first. So let's say b of n is equal to the number of partitions of n of this pink sentence type. But notice that the number of partitions of n of this pink sentence type is exactly equal to the number of partitions of n, or the number of polynomials that evaluate at 2 to give us n. And that's from this argument that we just made. Okay, great. So now what I want to do is make a generating function. So I'll maybe call this capital B of Q. And I want to point out, sometimes I get comments about how I write my Q. I'm not exactly really sure why I write my Q like that. When I was an undergrad in Arkansas, I went to the University of Arkansas at Little Rock. I had an abstract algebra professor that wrote her Qs like that, and I really liked her classes and stuff, so I think I was just copying her. Her name was Dr. Cassandra Cox. So if anyone's from Arkansas, goes to UALR, has ever had her in a class, maybe ping her an email and say that, you know, I'm still doing math or something. She probably doesn't remember me. Okay, so this is going to be equal to the sum, as n goes from 0 up to infinity, of b sub n q to the n. Okay, let's maybe translate this sentence into a generating function using the strategy that we outlined during the hints. So our first part of this will be 1 plus q squared plus q cubed. And I want to carefully point out that this portion of the generating function governs all of the parts of size 1. So I'll write that here, parts size equal to 1. And then down here, this will be equal to no parts. So in other words, if we take 1 as part of our multiplication, that's no parts of size 1 This right here will be 1 part of size 1, this q to the 1 power. This thing right here, which is q squared, will be 2 parts of size 1, and this thing right here, q cubed, will be 3 parts of size 1. And now we're just going to continue that on and on and on. So next we're going to want parts of size 2, and we'll have 0, 1, 2, or 3 parts of size 2. So that's going to be 1 plus q squared plus q to the 4th plus q to the 6th. So I won't lay that out like I did down here for the first one, but it's the same kind of thing. Then I want parts of size 4. So I'm going to have 1 plus q to the 4th plus q to the 8th plus q to the 12th. So that would be 0 parts, 1, 2, 3 parts of size 4. But now this is going to be an infinite product of all of these terms. Okay, so we've gained a generating function that can help us solve this problem. I'm going to go ahead and clean up the board, and then we'll find a nice closed form for this generating function. Okay, on the last board we got to the following point. We set b of n equal to the number of partitions of n satisfying some rules. So those rules were laid out on the last board. And we also argued that that number was the same thing as the number of polynomials satisfying these rules over here in the setup of our problem. Next, we found the generating function for the sequence b of n was equal to this thing that we called capital B of q, and we denoted it by the sum n goes from 0 to infinity of b of n q to the n, and then 1 plus q squared plus q cubed times 1 plus q squared plus q to the 4th plus q to the 6th, and so on and so forth. And I also gave like a little tidbit of why I write my q's like this. Maybe another question to answer is why use q in the first place? And that really takes motivation from Ramanujan. So Ramanujan did a lot of famous work with integer partitions, and he almost always used q for the generating functions involving integer partitions. So this is like a little nod to his work. Okay, so now we're going to simplify this right-hand side a little bit by seeing each of these terms as quotients of polynomials. So let's maybe look at this one first. We can write this as a quotient of 2 polynomials. It's going to be 1 minus q to the 4th over 1 minus q. So I'll let you guys think about that, but that's like a pretty standard way to write this 1 plus q squared plus q cubed. It's kind of like a finite geometric series or something. Good. And then now let's go ahead and look at this one. So we can do the same kind of thing here. So this is going to be 1 minus q to the 8 over 1 minus q squared. Okay, and then let's see what this one is going to give us. So that's going to give us 1 minus q to the 16 over 1 minus q to the 4th. And now I think we can see where we're going. So notice we've got 1 minus q squared, 1 minus q to the 4th. So we've got powers of 2 happening in the denominator there. And then we have 1 minus q to the 4th, 1 minus q to the 8th, 1 minus q to the 16th. We also have powers of 2 rising in the numerator. So maybe I'll write the next one down. That's going to be 1 minus q to the 32nd over 1 minus q to the 8. Good. And this is going to be an infinite product. But the nice thing here is that this is a telescoping infinite product. So notice our 1 minus q to the 4th is going to cancel with this thing that is 2 steps further and in the denominator. Our 1 minus q to the 8 is going to cancel with this thing that is 2 steps further and in the denominator, and then so on and so forth. So every term in the numerator has a related term in the denominator that can be canceled. But we're left with this 1 minus q times 1 minus q squared in the denominator. So now let's go ahead and bring down what's left over. So I can write this as 1 over 1 minus q. And then I'm going to go ahead and factor out this 1 minus q squared as a difference of squares. So I have 1 minus q times 1 plus q. Good. And now what I want to notice is you can do a partial fraction decomposition on this, one of a lot of different ways. So I'll just sketch out maybe what would be the most common way to do it. So we could write this as a over 1 minus q plus b over 1 minus q quantity squared, and then plus c over 1 plus q. So that's like a standard fact from like integration techniques. And I'm not going to calculate those a's, b's, and c's. I'll let you guys do that. I'll just jump to the point where we have it in a form that is nice and simple to expand. So this can be simplified to 1/2 times the quantity 1 over 1 minus q squared plus 1 over 1 minus q, all of that squared. But now this first one can be expanded via geometric series. This second one can be expanded one of two ways. You can either use the binomial theorem, or maybe better yet, we could notice that it is the derivative of a geometric series. So I'm going to write this as 1/2 1 over 1 minus q squared plus the derivative with respect to q of 1 over 1 minus q. Now we can expand this thing as a geometric series and do term-by-term differentiation. I think that's a bit easier than expanding it as a binomial with like the power of -2. Okay, so I'm gonna go ahead and bring this up to the top and then we'll move towards the end. So far we've set b of n equal to the number of polynomials p of x satisfying these rules over here. And I want to point out that that's equal to the number of partitions of n satisfying some rules that we did earlier. And we've got a nice generating function for this sequence b of n. So we called it capital B of q, and it was equal to 1/2 1 over 1 minus q squared plus the derivative with respect to q 1 over 1 minus q. Now I want to expand these as geometric series. So that's going to give me 1/2. Can expand this thing as a geometric series pretty easily. That's going to be the sum as n goes from 0 to infinity of q to the 2 to the n. In other words, q to the 2n, like that. And then next, I have the derivative with respect to q, and then the sum as n goes from 0 to infinity of q to the n. Because there my common ratio is just q instead of q squared. Okay, nice. So now let's go ahead and simplify this bit right here. So I'll just bring this down. This is the sum n equals 0 to infinity of q to the 2n plus, now I can rewrite this as the sum n equals 1 to infinity of n times q to the n minus 1, like that. Okay, nice. Now I'm going to go ahead and re-index this thing a little bit. And the reason I'm going to re-index it is so that I can get this being a q to the n power instead of just a q to the n minus 1 power, so that these can match a little bit better. So I'm going to go ahead and here replace n with n plus 1. That's going to make me start at 0 instead of at 1. And then also I'm going to split this thing up into two sums. But really one of the sums is just a sum of a bunch of 0 terms. So notice I can re-index this by sending n to n over 2 if I only sum over the even elements. So I'll get 1/2, and now I have the sum n equals 0 to infinity of q to the n, but now I'm going to require the condition on this sum that n is even. Notice I haven't gotten rid of anything here because there are no odd powers of n in this first sum. So this sum is exactly equal to this sum. It's just re-indexed in a weird way. Now I'm going to go ahead and do this change of index and the same kind of even odd thing in this one as well. So that's going to give me plus the sum n equals 0 to infinity n even of n plus 1 q to the n. So that would be doing this pink re-indexing and splitting it up into even and odd cases. And then plus the sum n equals 1 to infinity. And here this will be the odd cases, n odd. And here we have n plus 1 q to the n. Great. So notice that these two sums right here can be mashed back together with this sum via the re-indexing that I've written right there. Okay, so now we're almost done. I'll go ahead and bring this up and then we'll finish it off. So now we're almost home free. I've got the generating function of b of n can be expressed as the sum of these three infinite series. So next I want to notice that this first sum and this second sum are indexed correctly, and they're summing over the same kind of thing in a way that we can add them together. And I want to notice that by q to the n here, I really mean 1 times q to the n. So that's going to easily add with n plus 1 times q to the n. So if I add these two that I've underlined in yellow, I'll get 1/2. And now I have the sum, as n goes from 0 to infinity, of n plus 2 q to the n. And I want to point out that these are the even values of n, and then plus the sum n equals 1 to infinity of n plus 1 q to the n. And I want to point out that these are the odd values of n. So now extracting coefficients from this side of the equation right here and then this side of the equation right here will allow us to get our number b of n, which is essentially our solution. So let's notice that we can write b of n in the following piecewise manner. So this is going to be equal to 1/2 times the quantity n plus 2 if n is even. And this is going to be equal to 1/2 n plus 1 if n is odd. And so that's a good place to stop.